So, hello everyone. As you said, my name is Pat Ryan, Chief Architect today. Could be something else tomorrow for SPR. A couple things I'd like to just address first. One is this really is the first time I've done this virtually. So if something doesn't look right or you can't hear me, feel free to get my attention in the chat window. So I'm presenting here, but the chat window's over on the side, but I'll try to, or just give a shout out to get my attention. So if something doesn't look right, let me know. It's the first time I've done this virtually. In terms of the video camera, I'm going to be kind of going on and off video camera because I do have some computer vision examples. And for that, it needs to use that camera. So if you see me going on and off, that's why. And this presentation is run out of something called a Jupyter Notebook because I'm not a huge fan of PowerPoint. So what I've done is tried to create a presentation that I can run out of a Jupyter Notebook, which is very much like a web page, but it actually allows me to run some code at the same time so you can see it live. And the whole reason for this presentation is to give people that introduction to machine learning, a little bit about what machine learning is, but then I really wanted to show some examples. They're generally simple examples, but I wanted you to actually see it working to give a really good sense of it. And so that's the whole idea. This is really about examples. I probably have more examples than I have time for, so I may make some time judgment calls and skip over some of them. So let me start also with, so I actually think we could do this all over again and just start with the question and have an entire discussion panel on just the answers that came back from the questions. I thought the insights and the fears and the observations were really spot on. And I'm gonna try to touch on some of these as we go. And for me, I think one of the things that scares me the most is that machine learning, if I just distill it down, in some ways, it's just this amazing pattern matcher. It can look at a bunch of data that you or I as humans might not be able to see the patterns in, but the machine learning algorithm will find it. And so it will be really good at exposing past behaviors that we may not be all that proud of. And that gets to a lot of the things you were talking about with the bias. And when Adam was talking about explainability, that is like spot on. It's a huge area of research. And as somebody else said, I also like to say, this is a tool. So someone was talking about the hammer. I could build a house or I could tear it down. This tool can be used for great good or great harm. It's a tool in our hands. And so we should be really thinking about how we're going to be using this tool. All right, enough of that. Let me start. And again, if you can't see it, if I'm going too fast, please let me know. All right, so the first thing we're going to do is spend a little time on the introduction to machine learning. This is sort of lecture-y and there's pictures and I talk to them. But then we're going to get into some examples. And like some of the examples, I got this really lo-fi 8-bit example of autonomous driving. We might look at some image classification. There's some on here that I'd like to show that's not even on this list just yet, but we're going to cover a fair number of different examples. And so for those of you that would like to get a non-technical perspective of where AI is, today, who sort of controls it and where it might go in the future, there's a book that I really loved. It's probably a year and a half maybe old, but still very relevant, called The Big Nine by Amy Webb. And she looks at the big 9 companies that really control artificial intelligence today and where it could go in the future. And she paints, an optimistic, a pessimistic, and a realistic view of where it could go. So if you'd like what I think is a fascinating read that's not technical, I highly recommend the book called The Big Nine. I don't think you'd be disappointed. You might be a little scared, but we should be aware and maybe a little scared. So I know machine learning and AI is like the big shiny toy of the day. It seems to get most of the bandwidth, but machine learning really is really old. probably further back than what I'm showing on this timeline. But I really think of Alan Turing as sort of the godfather of it all, even though before him, clearly, there was work being done. And so a lot of the mathematics behind machine learning that we use even today, the algorithms that we use today, some of them were actually developed back in the 50s and the 60s. It really is the fact that compute power has caught up to allow us to churn through all of this data. And so my takeaway from showing that timeline really is to give you the sense that it's not really a shiny new toy. It's really been around for a long time. Most of the mathematics I said here has been around between 1930 and 1974. There's this time period that they call the AI winter for about 20 years, because when it first started out, people were super excited about machine learning, but the compute power wasn't there. So there was a fair bit of disappointment that it didn't pan out to be what it could have been, what it was advertised to be. So it went into this 20-year AI winter. And it's not really, except for the past 20 years or so, that it's accelerated because of the compute power. So we're leveraging the minds of the past and marrying that up with the hardware of today. And that's really where we are at with machine learning and artificial intelligence. All right, so let me break up artificial intelligence, machine learning, and deep learning. So artificial intelligence, I think of it as that overarching computer science field. I think of it as like when someone says they're in biology or they're in chemistry. So it's that overarching branch of computer science that we focus on how can we make decisions with machines. Now, I know we like to call it artificial intelligence, but when I think of AI, I like to think of it as augmented intelligence. So these are great algorithms and they can help us solve very complex problems, but they should be augmenting our human intelligence. Like someone who was saying that one of their fears is that basically this is just going to start taking over and we're not going to understand the hows and the whys. That's why I like to think of it as augmented intelligence for now. Machine learning is a subset of artificial intelligence. And there's a couple of great definitions, but machine learning is also known as narrow AI, because what we're going to do is train these machine learning algorithms to focus on a very single task. We're going to make them really good at telling the difference between a cat or a dog, or figuring out who's going to churn, or whether an X-ray is cancer or not cancer. But once you train a machine learning model to understand how to do that, that model can't be used for anything but that. And that's why sometimes you'll see it in the literature as narrow AI. And I know sometimes AI and ML are used interchangeably, but I don't see that as correct. So then deep learning is yet another subset of machine learning, where we're actually going to be looking at a different way to set up the algorithms called neural networks. And the deep part of that refers to, I'm going to show you a picture of this in a second so it'll be clear, but it really refers to the number of hidden layers between the inputs and the outputs. But it's still narrow. And so artificial general intelligence will be maybe someday that point in time where the machines are not just focused on a narrow task. Like us as humans, we might be able to drive the car and tell the difference between a cat and a dog. Well, today machine learning algorithms are created to drive a car, but they can't tell the difference between a cat and a dog. Artificial general intelligence is that it starts to broaden what it can do. I don't think that's any day soon, thankfully.
Pat?
Yeah.
This is Pat Maher. Can you do me a favor for any of our guests with vision loss to any extent? If when you show a visual, if you could just at a high level verbally explain that?
Oh, sure.
That'd be great. Thanks.
Yes, and if I'm not doing it justice, help me out, Pat. Okay, so in terms of what that means for software development, it's really a fundamental shift. So as I grew up in this industry for the past 30 years, I have always been given a certain set of input, and my job was to write a program, as it says, a very purpose-built piece of code to generate the outputs that they were looking for. So on the left, I have this image which shows inputs going into a box, and then the program that I write going into this box, that's the purpose-built code. And then the output of that is what the piece of code was meant to produce. However, with machine learning, it's very different. It sort of turns itself inside out. I still start with the same set of inputs, but now I'm going to collect the outputs that I'm expecting. And the focus becomes training the machine learning model, and that becomes the program. And so instead of focusing on writing a lot of code, really the focus shifts to collecting the right kinds of data to produce and to predict the outputs that you were looking to get. And so what kind of problems can be solved with machine learning? I like to say this all the time. Any problem that can absolutely, positively be wrong sometimes. We've talked to numerous clients because they don't have an awareness yet of what this technology is, but machine learning revolves around probabilities. And so you cannot use machine learning to move your money across your accounts. That would be a very bad thing. So if it's okay to be wrong sometimes, then machine learning can be used. But if you cannot be wrong sometimes, then you cannot use machine learning. And sometimes being wrong sometimes and being right all the time, that's a very gray area. So somebody was mentioning cars and like what happens with the autonomous cars if somebody jumps out, how is the car going to respond to that? And so you can think of it as, it may not be perfect, but does it behave on average better than the general population? So it's still wrong sometimes, but is it better? And if we're going to talk about wrong sometimes, it's not just about whether I'm 97% accurate. So for example, if we look at 2019 breast cancer estimates, if we have an algorithm that can detect breast cancer at 97% accuracy, and that sounds like a fantastic percentage, and it is actually a fantastic percentage, but that's going to leave a certain number of people misdiagnosed. So the question becomes, well, how were they misdiagnosed? Was it a false positive or a false negative? So if it was a false positive, that means we falsely said you had cancer, but you really didn't. And so while that outcome is scary, that's better than saying we falsely said you didn't have it, but you actually did. So when you go through the training of models, it's not enough just to understand how accurate the model is. We have to look at how it got the answers wrong. And then you can start, depending on your what problem you're trying to solve, you can then start to shift it to maybe give you more false positives or more false negatives. It really depends on your business problem. But just keep in mind, when someone says something has a certain accuracy, we need to go dig deeper. We need to understand how it got the answers wrong. And so I like this definition. I attribute it to Andreas Müller, who is the author of Scikit-learn, but I'm sure this came from somewhere else. So machine learning is the art and science of giving computers the ability to learn to make decisions from the data without being explicitly programmed. And that gets back to what I was talking about before. It's changing the whole shift of how we develop software. I'm not going to explicitly program to look for these patterns. Instead, I'm going to collect the data that represents my problem and then train the model to recognize those patterns. So it's a completely different mind shift on how we solve the actual problem that we're trying to solve. And I have a Venn diagram. One circle represents computer science in the upper left. The other on the right, in the upper right, represents sort of the math and statistics field. And then the circle on the bottom represents that business domain. And where machine learning lives is in that circle between the overlap of computer science and math and statistics. Because it's going to take both the math background to understand the probabilities and the statistical analysis, along with the computer science people to actually build the code to run it, to create the machine learning algorithms. And at the very center of all the overlaps of computer science on the upper left, math and stats on the upper right, and business on the lower portion, when all of those cross over, that's where you have your data scientists. Your data scientist can understand the code that went to build the model, the math that backs up that code and that particular model, but also understands why it's important to the business. What is the business going to do with this information? So we're talking about machine learning today, and that's the computer science and the math. But as soon as you add someone that understands the business, now you have a data scientist. All right, so I'm going to talk about, there's lots of different types of machine learning, so I'm going to keep it a little bit high level. But there's essentially, I classify it as two major types of machine learning. There's machine learning, and then there's deep learning. In the picture that I'm showing here, on the top left, on the top, I'm going to talk about what the machine learning process looks like. On the far left, we start with our inputs. The inputs could be data from a bank. It could be an image. It might be data from a sensor. So we always start with our inputs. The next layer is called feature extraction or feature engineering. And this is typically where machine learning engineers, data scientists, business people will get together, look at that data, and decide how we need to change or manipulate the data to get the answer to the question. So for example, part of that job is to look for missing values. Maybe we have to change string values into numbers, or maybe we can look at various inputs and create yet a third way to look at that data and add that to the machine learning model. But there's a lot of human interaction with that particular process. And then we'll typically run it through machine learning algorithms, for example, like through scikit-learn, to produce our outputs. Now, deep learning is slightly different. And that's the bottom part of the screen of the image. And on the far left of that one, I still have the exact same inputs. So the inputs really don't change. But the layers between the input and the output is what we call those hidden layers. So the feature extraction and the learning layers, the green here and the yellow in the center, those are the hidden layers. And in deep learning, you don't really have the feature engineering phase of this. The very first layers of a deep neural network actually do a pretty good job of figuring out what features are important, what combinations of features are important. And then later in that network of nodes, it starts to learn how to map the inputs to the outputs. In some ways, I'm still a little bit amazed that you can create an algorithmic architecture that looks like a bunch of fully connected nodes. And each one of those lines has a weight. So every time a number goes into it, it gets multiplied by a weight, and there's a mathematical process. But in the end, it figures out how to map arbitrary inputs to a set of outputs. Now, if I break down the machine learning part of this, not the deep learning part, but the machine learning part, I'm going to break it up in machine learning into three primary areas: supervised learning, unsupervised learning, and then reinforcement learning. And the picture that I'm showing here, the upper right is looking at different ways we could do supervised learning. And I'm going to break supervised learning into classification problems, which are things like image classification, what's in that image, or regression type machine learning. And that could be figuring out a home price, for example. But the idea behind supervised learning is that I've been given the answers. I know the inputs, and I've been given the answers, and now I'm going to train a model to recognize how to take the inputs to the outputs. In unsupervised learning, I don't have the answers. I have a lot of data, and I'm just trying to figure out how this data relates to one another. And one of the typical examples is clustering. And we've worked with clients to do this, where we want to understand how, if I have 100,000 customers, how do these customers sort of cluster together? You and I looking at the data won't understand why certain customers come together and why certain ones don't. But the clustering algorithms, the unsupervised clustering algorithms will figure out the similarities in the data and tell us that this group of the population, they are similar. It'll be up to us to figure out how and why they're similar, but the algorithm can find those patterns that make them similar. And then reinforcement learning is yet altogether different. Reinforcement learning uses this thing called a reward system, where you allow something to work in an environment, and every time it does something good, you give it a positive reward. If it doesn't behave properly in the environment, we give it a negative reward. It's a little bit like owning a puppy. All right, so the steps that we like to go through on a typical machine learning problem is we have to gather and clean the data, which typically is a very large part of the problem. We have to do the feature engineering and the feature selection. And that is probably iterative. You're going to get data, you're going to clean it, you're going to think you have the right set of features, and you're going to find you don't. Then you select a machine learning model. And there's so many to choose from, and there are various techniques to figure out what's the best model. There is no one good machine learning model. The machine learning models seem to behave and interpret the data differently. So one type of machine learning model might do great on one set of data and not so good on another. But this is why you have to, because they all have different characteristics. So that's why you have to look at different machine learning models to see which ones can find the patterns in your data. So you then train your model, and if we're doing supervised learning, you'll have the labeled data. Labeled means I have the answers. So it's almost like giving it an exam, right? I'm going to train it on the data. I'm going to give you the answers so you can learn how to take the input data and figure out how to get the output. And I'm going to test it. And I'm not going to give it the answers. And that's what I'm showing here in the train test split. So we take all the data that we have. I break some of it up into training data, which I use to train my model. And I have some of it as my test data that the model never sees. The training data has both the inputs and the known outputs. This is like your practice exams, or as you're going through learning new material in school, it's the same kind of idea. However, the test data is sort of that final exam. The teacher has the answers, but we're asking the model to tell us what it thinks the answers are. And then we compare the answers that we know to be true with the predictions that the model came up with. And this is a very iterative process, and we will keep doing this testing until we get an accuracy or a metric. There's a lot of different ways we can measure machine learning models until we get that metric that meets our goals. All right, so there's the whirlwind machine learning overview 101 really fast. So now I'm going to try to jump into examples. So I hope that sort of laid at least some groundwork for us. And now I'm going to try to put some of the words that I just said into actual practice. So the first example I'd like to show you, I call it an autonomous driving example. We're not really going to use a Tesla Model S. I think of this particular example is like when 8-bit Mario meets high tech. And so what we're going to do is I'm going to show you in just a second, but I've got a screen that looks like this one in the center. It has a simulated car, and we're going to train it to drive on this simulated road. So let me switch over to here. I'm going to run a Python script that will bring up the road. I'm going to press, let me go ahead and get that started. And so I don't know if I can make that any larger. Can I? Well, maybe I can. Okay, good. I hope that's easier to see. So the set of cursors that is red and that yellowy orange, that's the car. And if you be creative and imagine it's actually driving on this road, what we are telling it is that no matter how the road looks, the right answer is to go straight. And so every time the road moves, we are actually sort of taking a snapshot of what that road looks like. I'm going to show you the data in just a second. And we're telling it that when the road looks like this snapshot, here's what you need to do to drive the car. And right now we're saying always go straight, which we know is not going to be the right answer. But then I'm going to show you how we can do this again and actually train it. All right. So now I'm going to train that. And I run through 3 different types of algorithms, and I look at a few different parameters. Now, this 1.0, that's the accuracy. So it's for any of the algorithms that I have selected here, it's saying it was perfect. It was able to perfectly predict, no matter what the road configuration looked like, what it should do. And that's because I only told it to go straight. I only had one answer. So of course it's going to be perfect. But let's see what happens. And the model now thinks it's awesome. So now let's try to actually use that model to drive. And I actually did build a model. I saved it to the hard drive, and I'm actually going to use this model to do the actual driving. So let's drive by model. And this time I'm going to use a random road. So now the model, based on what the road looks like, is predicting what the right answer should be. Well, and because we said you should always go straight, and again, the model thinks it's doing awesome. So it doesn't know that it's actually terrible. So every time the road moves, it takes a snapshot, it sends that snapshot into the model, and the model comes back and says, I predict the right answer here is to go straight. And you can see it didn't take very long before we were completely off-road. Now let me do the same thing. This time I'm gonna actually train it. So I am gonna be using my cursor keys, and I have good days and bad days when I drive this thing. So let's see what happens. All right, so now you can see as I'm driving on the road, yeah, I hit the shoulder. Interestingly enough, when I do this at companies, I usually have somebody from the company come up and do the actual driving as I'm doing. So I'm just hitting the left and right keys or going straight to simulate me staying on the road. Every time the road moves, it's making a note of if I told it to go left or right or straight. So when I do this at companies, I would have to say that most employees don't do a great job at driving this simulated 8-bit, but when I go to high schools, they're amazing. So it's all the gaming these kids do. All right, I've collected all my data, and I really am collecting data. I'm going to show it to you in just a second. So now I am going to do my model training. And again, I'm going through the exact same models, except this time I'm not getting perfect scores, which is what I would expect. So now I've gotten 93% accuracy, 93, about, like they're all the same. Oh no, one's about 91. So I'm going to use the best model, and I'm going to ask it to drive by this new model. Although I can't quite see it. There we go, drive by model. All right, I'm going to do the same sort of random road. Now, remember, it's only 92% accurate. We should expect it not to always work, but now it's the model. See, here's my hands, I'm not driving. Now the model is looking at the road, and based on the training data that I gave it, it's looking at the road configuration and saying, well, my best prediction based on what you did before, and then it sends that to the to the output to actually move the car, if you will. So now it's doing pretty well. Every now and then, sometimes it'll go off the road. But it's not me doing this now. We actually trained the model to look at this data and figure this out for us. So this one did pretty well. Sometimes it goes off the road, but this one did pretty well. And that was all just using some very simple data. Let me show you what that looks like. All right, so now, so left will be noted as a 0, straight will be a 1, and right will be a 2. And I know it's a little hard to see, but column 0 is basically how I should be steering. So, but this is what the data looks like. It's just a bunch of 0s, 1s, and 2s. And if you can imagine trying to sit down and write a program to find this pattern, it would be super hard. Let me take a look at what this one is, right turn, what it looks like. And I've reconfigured the data into a matrix. So this actually looks like the road that we saw just a second ago, but in matrix form. And visually, I can sort of see the 2s. The 2s represent the white road, the black represents off-road, and 1 represents that grayish shoulder. So we can see the pattern pretty easily, but for us to write code to see this pattern and then generalize this to patterns we haven't quite seen yet would be really difficult. And this is where I think machine learning shines. It can find these patterns for us. Let me just show you a couple more. This one is straight. So if you can look where the 2s are at, if you imagine the cars at the bottom, the right answer would be to go straight for a little while before I have to turn right. And then just left is the same thing. If the car is at the bottom, the right answer here would be to start turning to my left until I got to that bend, then I'll switch it back to a right. So the idea of showing you this one is a very simple, relatable. I actually trained this 8-bit car to be able to drive on that road just by finding out these patterns using very simple machine learning models. So I know some people think, oh, don't I need a ton of data? And is it super hard? And it's, you know, I can't do it. But we actually, it's to the point where we can. This just runs on my machine. There are problems that require big data, lots of data, heavy duty machines, but there's a lot of problems that we can solve right from our laptops. All right, I'm gonna switch gears a little bit. I'm gonna go into image classification. So with image classification, typically that is what we think of as a deep learning activity. A lot of computer vision and deep learning algorithms, they go hand in hand. I'm gonna do something a little different. I'm gonna look at image classification from the machine learning perspective, and I'm just gonna look at a picture's, the amount of red, green, and blue that each of these pictures has in them, and then create some additional features. This is that feature engineering I was talking about before. So I'm gonna see if just looking at basically the red, greens, and blues of a picture, can I figure out, is the picture a picture of a coast, a forest, or a highway? And then there's another data set that I want to see, could I do the exact same idea and see if something is a picture of a cat, a dog, or a panda? So let's see. And you might be thinking, why is this detail of how I'm collecting the data and using the data in my machine learning so important? Well, this gets to some of the discussion about explainability. When this machine learning model fails, we have to know, well, what was the data that went into the model? What is it looking at? What attributes is it trying to pull out of the data, and the patterns is it trying to find? So having an understanding that I'm looking at color distribution will help me understand why a machine learning model might fail. All right, let's look at what we're trying to do for this one. So we have 3 scenes. The upper left is just a collection of coasts, and I just give you a smattering of examples so you can get a sense for what they look like. The center is of highways, and again, it's just a collection, a montage of those, and then forests. And I took 3 pictures out. I took a random coast and a random highway and a random forest out of that data set. And remember, I do that because I want to have the data, the image that I use to predict on, the machine learning model cannot have seen that ahead of time. That's like giving the answers to a test to somebody. Can't do that. All right, let's take a look at what those pictures look like. So if I look at each one of those pictures, coast, highway, and forest, in the center, I'm showing you the color histogram, the amount of red, the amount of green, and the amount of blue in the actual pictures. Now on the far right, I'm showing you, basically I'm creating these buckets of color, and I'm just grouping them together because it's much easier to work on a bucket of color than it is on that continuous value. So what's going into the machine learning model is the values on the far right where it says flattened bins. That's the numeric value that goes into the actual machine learning model. But here's what I'd like to point out. When I look at the coast, I can see that there's a fair bit of blue in there, and I can see that in the histogram. The histogram, the blue is, it's the highest overall value, if you will. When I look at the highway, it's not a really good picture. It looks like an old picture, actually. It's a little yellowed, but there's also a lot of green in that particular picture. And we can see that just by looking at the histogram. Seems like there's a fair bit of the green color in this one. And the forest, which I expected there to be more green, but this is a very dark picture of trees in the forest. Almost a picture of a canyon more than it is the trees. But we can see that there's not a whole lot of color in here. So this one I think is going to be an interesting test case. So let's see how it works. All right, one quick view of the data. So I've taken each one of those pictures that I want to take a look at, and I just want to give you a sense for what does that data look like. It's just a table of numbers. And again, just to sort of impress that if we had to write the code to do this, finding the pattern in those numbers would be super hard. Let's take a look at cat, dog, and panda. I'm going to do the same thing. So I picked some of these because I thought, well, this cat picture also has a person in it, so that's going to change the coloration of it. The dog picture that I have also has a person in it, so that could be changing the color of it. And then a panda, which is a black and white, but it also has the tree that obstructs it. But remember, since we're looking at color distribution, any obstruction that we see visually probably doesn't come into play for the machine learning model. And interesting, like for something like a panda, and in this particular picture, we can see that most of the color is at the black, close to 0 in terms of pixel intensities or black, or it's on the far right, which is close to white, which would make sense. So let's see how these. Oh, here's the cat, dog, and panda. Again, the same kind of numbers. You and I looking at it can't make sense of it. Let's see how these models perform. All right, I'm going to try to send that coast picture into models that I've already created. So I'm not actually creating them this time like I did with the carb, because these take a little while. And this model was actually able to say that this particular picture was most like all of the other coast pictures. Just looking at the color distribution. Now, it doesn't always work. And the highway one was also really good at figuring out that particular picture based on all the color distributions for all the other highways. It was most like a highway and not a forest, for example. And if I do for the forest, it was actually able to figure this one out too. This one surprised me. I thought this would be a tougher one, but it actually worked out for this particular image. So on the scenes, it did pretty well. Let's see how it does on the animals. This one, it gets wrong. Now, the question would become, why did it get this one wrong? Well, since we knew that we're looking at color distribution, that gives us a place to start to understand and dig into how we can figure out why the machine learning model got this wrong, which is why I spent some time up front going over how we created the data to feed into the model. And these others, it actually does pretty well with these. But here's my question. What if I send the highway picture into the model that is used to predict animals, the cat, the dog, or the panda? what happens if I put in a highway picture? And this gets to the whole narrow AI. We created a machine learning algorithm that understood how to tell the difference between a cat, dog, and a panda. If we give it anything else, it's going to do its darndest to say that that is some kind of animal because it's very narrow in scope. And so this particular case, it actually says, well, that road is most like a panda. And my guess on that one is that there's a fair bit of light color in all this one. Again, this is also why we go over what it is, what data went into the model. And then I just grab a random cat, and it's a cute cat, and sure enough, it was able to figure out that it was a cat. Now, as I said before about the color distribution, that's not how we do image classification. We use deep learning models. But there's still a lot of data, there's still a lot of insight just by looking at the color distribution. All right, so now I'm going to get to one that scares people. This came up a couple times, facial recognition. So let me kind of go over how this works. Oh, I'm going to come off a camera because I think I'm going to need my camera in just a second. You should still be able to see my screen. So with facial recognition, basically the pipeline is this. We're going to grab an image. We're going to detect where the face is. We're going to look to find points of interest on that face and crop the face out. That face goes into a deep neural network that produces on the other side of it this array of numbers, 128 wide. So it produces 128 numbers. And now you might be asking, well, what are those numbers? And the reality of it is, we have no idea. It's the output of the model is this array of numbers that represents that face. And only that face will have the collection of 128 numbers. And so it starts with what we call these 68 facial landmarks. And so there is a way to take the picture of a face and look at what the facial landmarks for any face is going to be. Let me see if this one works. Live coding, let's see. Oh, it worked, excellent. So this is actually taking the feed from my video camera and running through the algorithm to find the 68 points of facial landmarks on my face. And these 68 points can then be fed into a machine learning algorithm to then determine that, yes, in fact, that was Pat. And in fact, that's what I've done here in terms of a facial recognition. And this is normally, if we were live, I actually bring somebody up and if they're comfortable with it, we will actually get them to train their face and have the facial recognition tell them all within about a minute and a half. It's that simple. It's that fast. And literally, I need one picture.
Pat, this is Pat. Can you explain to any guests with vision loss what they're seeing now?
Thank you, Pat. Yeah, so I have got my video camera turned on. So you're actually seeing my live face. It's a live stream. And I'm running every frame of this video through a machine learning algorithm that's figuring out what this face, who does it represent? And I've already trained it to know my face. And so it's overlaying a square box over my face. And a lot of times it uses those 68 points, or there's different ways it can figure out where the green box around my face should be. And at the top of that box, it has my name. So
Thanks,
it's using
Pat.
a lot of facial recognition, using a lot of facial landmarks, and it's going to draw a square around it. And I tell you, it's unfortunately super easy to do. So if someone that said that this is one of the things they were frightened of, it's a legitimate fear. But let me show you how we can use it. There are upsides to this technology, right? As I said, it could be used for great good or for great harm. What if we wanted to use it for mask detection? We could do the same kinds of things. This is using a deep learning model to actually look to see if we have masks on. Maybe we wanted to have that at the storefront, so we can make sure we have masks before we enter. So we can do the same kind of a thing. I'm not sure which screen this is going to pop up. Guess it's going to be over here. All right, so I've just did the same sort of a thing. I now have a screen that is showing a live feed from my video, and it's created a red box around my face, and it's been trained to tell me whether I'm wearing a mask right now or I'm not wearing a mask. The red box around my face indicates that I have no mask, and it's absolutely certain I have no mask. If I grab a mask and I go ahead and I put that on, I know you probably can't hear me as well, but now it's saying with a high degree of accuracy that in fact I am wearing a mask. So we can still use this technology that we find scary for something that's good. And as soon, oh, if I don't lose my earbuds, as soon as I take that mask off, it tells me I'm not wearing a mask. Okay, we have 20 more minutes. Is that right, Pat?
Yeah, that's correct, Pat, but I'm sure many members or guests would stick around if you run a little late.
Okay. Okay. Well,
Your
let me
call.
continue. Let me continue on. As I said, I have all these examples that I can do in a half-hour presentation or a 2-hour presentation. So let me go through this. We talked about bias. So I am going to look at a very simple data set called the Titanic data set. It's one of like the very first data sets you'll likely look at when you get into machine learning. And I have to tell you right now, there is a spoiler alert. So if you don't know how the Titanic ends, you might want to just turn off the audio for a minute. All right, so we're going to try to predict if Rose and Jack survive the Titanic. And I'm going to go a little quickly through the data part of this so we can get to the back end of it. So we have the Titanic data set. There's a number of different features. And remember, the features are the things we're going to train on. And the label, or the thing we're trying to figure out, is this survived column. Did you survive or did you not survive? And so we have things like the passenger class, your name, the sex, the age, whether you were traveling with siblings or parents, the fare, how much you paid for your ticket. So there's a lot of different things that we know about everybody on the Titanic. So now Rose was female, age 17, first class passenger, probably paid a high fare. So we'd like to find her in that data set. And if I look for people with that particular set of demographics, I find 2. So I'm going to take passenger, this 229. Jack, if you recall, I think he won his ticket in a poker game, if I recall from the movie. So Jack was male, 20 years, probably a third class passenger, low fare. Let's see who matches that particular data. And there's a lot of them. So I'm going to go to the bottom and just pick 673 as the person that's going to represent Jack in our story. All right, so the first thing we need to do is pull those records out, because I don't want to train a model that actually has that. It'd be like giving everybody the answers to the test. All right, so we're going to set up our machine learning model. We're going to use 6 different columns or features, if you will. And we have the survived column, which is what we're trying to predict. So let's take a look at Jack. Jack's data looks like third class passenger. Now sex is 0. Now let me just point out that when we create machine learning models, everything has to be a number. So even though the sex out of the data set was the string male or the string female, we had to change that into a number. So age 20, there was no sibling or spouse. It was just Jack. No parents or children traveling with him. It was just him and a very low fare. So we're going to use this data to try to predict if someone that matches that set of demographics would survive or not. And again, spoiler alert, in case you don't know, Jack does not survive. But now let's take a look at Rose. All right, Rose was first class passenger, female 17. Siblings or spouse, probably had siblings, parent and child, probably had a parent or child, but that was the person I used, and a high fare. So again, spoiler alert, somebody with that demographic, do they survive? And they do survive. Now, the reason I like to go over this example is not because I think this is a fantastic example of machine learning, but I think it's a good example of bias that's in the data. So let's take a look at a second class, someone in the passenger second class, 0 for male, 5 years of age, sibling or spouse, 2 parents, average fare. And we can see that a male 5 years old, second class, survives. But let's continue on here. What about a 9-year-old male? 9-year-old male survives. Let's continue on here. Let's take a look at a 10-year-old. 10-year-old male doesn't survive. What if we change that to female? A 10-year-old female does survive. So let's take a little deeper look at the data. And if we do a quick little analysis based on the passenger sex and the passenger class, we can see a couple things. One is that far more females survived than did males.
And again, Pat, would you be willing to note
thank you, Pat.
The graph? Thanks.
Yes. So the graph I'm showing shows 3 bars for female on the left-hand side and 3 bars for male on the right-hand side. The female bars are broken into a blue for the first class passenger, which is very high, followed by an orange bar, which is for the second class passengers, which is almost as high as the blue, followed by third class passengers. That's about halfway up. So what that is telling us is that females survived more than males, and first class and second class passenger females survived more than the third class passenger females did. On the right on this graph is for the males, and again, it's the same blue and orange and green. So the blue represents the first class males that survived. We can see no matter what passenger class the males were in, fewer of them survived than females, but first class passengers had a better chance. So let me just, I'm gonna do a couple more things here. This is a little bit of a busy graph, I realize. What I've decided to do was take the same female and male split. On the left-hand side, again, as all those bars represent female passengers that survived, and I broke them up in terms of age groups. Interestingly enough, I think it's interesting, of the female age group, those between over 51 had the highest survival rate. Those females that were basically 0 to 9, so the children, had the lowest. On the right-hand side of this image is all the males that I grouped them by age as well. For the males 0 to 9 had the largest survival rate. And if you think about this, back in the day, the saying always was, women and children first. And so this data really reflects those social norms of that day, that women and children get lifeboats first. And as you can see, even in the male side of this, the male children had the highest survival rate, at least in the 0 to 9 age particular group. So I like to point this one out, again, not because I think it's a great machine learning example, but when we talk about bias in the data, I think it was Adam that talked about data bias and model bias. So machine learning algorithms, and one thing I pointed out is it tends to, yes, expose past behavior. This is exposing a past behavior of women and children first. And so I know we talk about bias in machine learning models, and we immediately have a negative connotation to that. But I guess what I'd like to point out here is that sometimes the bias is really just reflecting the social norms of the day. And what we have to ask is, do those social norms of yesterday apply to the social norms of today? Because I don't think there's anyone that would argue that we have to change this machine learning model so an even number of males, females, and age groups die. So it's a really sticky problem, but I like to point this one out because I think this one, it's easy to relate to. So I hope I just didn't step on something really bad there, but that's why I like this particular example. All right, let's go to something a little more fun, games. Here I'm going to show an example of reinforcement learning. And this, I'm going to use this, we're going to build a game that's going to learn how to win by using reinforcement learning. Here's the game. The blue square, which is going to be a blue dot in the actual implementation because software versions change. So the blue dot or square, the job of this game is to randomly run around this game board and find the green square. When you find the green square, you win. If you find the red square, you lose. Now, the only thing we're going to tell the blue dot is how far away you are from the green and the red, but we're not going to tell it which one's green and which one's red. We're just going to say, here's distance to one of them, and here's the distance to the other. So from the player's perspective, that's what it looks like. I'm showing a grid here with a blue dot that's running around. You don't see any other dots, but its job is to find where on that square is the green one, where on this grid or this game board is the red one, and stay away from that one. So in the interest of time, I'm just going to fire it up, an example, and I'm going to talk to it. Okay, so I've just basically fired up this game. I'm showing a live example of this working. I've got a grid. That's looks like about a 10 by 10 grid. We randomly place a green dot somewhere and a red dot somewhere. And the blue dot is randomly moving around. Every time it moves, we give it a little negative reward because I want to minimize the number of moves that it makes. If it randomly finds the green dot, I give it a large reward. If it randomly finds the red dot, I give it a large negative reward. So every time it moves, it's collecting and it's making a note of how it moved and what the reward was for making that move. And so now we're coming close to the end of the game. Look at how it's doing this now. It's able to find the green dot and avoid the red one. You see that? It knew how to avoid the red one. And it learned this just from looking at just from playing the game and getting a reward of good or bad every time it made a move. And without me telling it to do anything, it's learned how to play the game in the environment through reinforcement learning of just a reward system. And just as a quick example, I have a graph here which shows the number of episodes or the number of times I played the game on the bottom and the amount of reward that it was able to find as it played the game. And as we played the game more and more, it was able to collect more and more reward. So it got much better at finding it. And then the next graph I'm showing shows, again, the number of episodes or the number of times I played the game at the bottom and the number of moves it took to actually find the winning square. And as we can see, it drops. The longer I play it, the less moves it needs to find the green square because I keep penalizing every little move. I give it a little negative reward. So it's trying to minimize that negative reward. All right, so I'm going to, I have one more example of that, but I'd like to switch over to something else. Something else that I've been working on. Now I'm really sort of in the deep end here. This is live, almost like live coding. I've been working on what they call a near real-time or a real-time object detection algorithm that will detect different sign language symbols in a real-time video feed. So what I've done is I've opened up my webcam. The window that I'm showing shows me. And what I'm going to do is do a few sign language gestures and run every time the frame comes through. I'm going to run it through the machine learning algorithm. It's going to see if anywhere in that frame it recognizes one of the sign languages that I trained it on. And if so, it's going to draw a box around it and tell me what it is. So if I do, there we go. All right, so this particular model is showing that I'm the sign language for hello. It's detected it in the real-time video feed, and it draws a box around my hand, and it tells me what sign language it is, and what the probability is. I also had it set up to, well, it's not going to do it. How about this one? How about that one? This is why live coding is so fun. Does it get this one? Hang on, let me come back down. Interesting. I wonder if I have too much light.
Oh, there it got it for a moment, Pat.
Well, how about this?
I love you.
Oh, there we go. All right. So, well, this sort of takes me to the end of my presentation. Normally, it's better than that. I don't know what's going on. Can I come back with it? Oh well. Text. Oh well.
No,
so this is the end of my
that's okay.
presentation, and so what I want to do is, so my goal here was to give you a little bit of background on machine learning, is show you some examples that that make it more real and hopefully make it more concrete for you. So my last thing for you is, and for your patience and your attention, and thank you very much. I appreciate that.
No, this was outstanding, Pat. Thank you so much. If anyone has questions, pardon me, Pat, if you'd be willing to entertain questions for 5 to 10 minutes.
Absolutely.
All right, that was outstanding. Okay, Brian, maybe you be willing to manage the Q&A session.
Sure. I saw Adam put his hand up. Adam?
Yeah, Pat, this one, let me echo what Pat Maher just said. This is fantastic. And are you able to share your Jupyter notebook, or is that proprietary?
Let me just double check with SPR. As far as I'm concerned, it's not proprietary, because there's nothing in here that has anything to do with client data.
Yeah.
So let me just check with.
Yeah, just find out, and if you can, great, and if you can't, totally understand. I just really love this presentation.
Oh, good. Well, thank you. If you have suggestions on how to improve it, I'm all ears. I love giving this one.
Chris?
Yeah, you can hear me, or can you hear me?
Yes.
The question, what I was going to say is, now I'm actually teaching assistive technology for the visually impaired folks, and one of the things I'm working with now is an OrCam camera. So it's a camera that attaches to glasses, and in real time it reads, and then if you train it with either facial recognition or products, it will tell you what the item is, that, or you could say, where are the stairs, and it'll find the stairs.
Yes.
But one of the things that I wanted to say for good, using facial recognition for good, so the person could train 250 people, and it'll say, mom is in front of you. But then I've worked with people where we don't have a face trained, and that's why I can see now why you have to say sometimes it's okay to be wrong, because it'll say, if it thinks it knows, it says a woman is in front of you, a man is in front of you, or a person is in front of you. And we've had sometimes the gender's been switched, but
Sure.
then, and which is okay, because this is just, we're in demo mode, it's not critical. But it's just interesting, the other day it didn't even pick a gender, it just said a person was in front of me, so I just wanted to say, yeah, so this device is there. Every edition we get, it has better recognition. So,
Yes. This technology is moving so fast. I feel like I am barely hanging on to the vapor trail of this technology. And the fact that, it's getting to the point of being able to tell you who it is when it's been trained on it, but also get the gender. It likely at some point could probably tell you aging of a person. But what it's likely doing is there's thresholds. And so if it takes a picture of a face, it'll look through all the faces that it knows. And if it doesn't pass a threshold test, then it probably drops back to, well, then can I just tell you what the gender is? And each of the genders probably have a threshold. And if it doesn't meet the threshold, then it's probably just person.
Yeah.
Right.
Thank you. And seeing your presentation actually, it gave me a new level of understanding. Thank you.
Oh, good. Oh, thank you. I appreciate that.
Liz?
Yeah, hi. That was again, I want to echo what other people said. Great presentation. I just have more of a high level question, and you're talking about you feel like you're holding on to the vapor trails. This stuff is advancing so quickly. So I guess from your perspective, what are some of the guardrails that you can use so that if you're working with a business or organization, they have both realistic and ethical expectations for using this type of technology? Because I really see some promise in the sense of, I love your description, computer science is overlapping with statistics. I'm learning statistics, and anything can help do the statistics faster for me. Yeah, I'm all for, and I do a lot of UX research, things like that. Sure. But at the same token, it's like you want to make sure their research is being used to inform decision making, not drive decision making, as well as not using the information you're collecting for the wrong purposes. You want to use it for the powers of good and not evil. So any ideas, like just high level guide rails that you can kind of put in place to make sure you don't go off course?
Wow, that is such a great question, and really hard to.
Sorry about that. It's late.
Man, really answer. But a couple things come to mind. One is there's this saying. I know I'm not going to get it exactly right, but it's basically we're going to torture the data until it tells us what we want.
Yeah.
So I see that happening a lot, and instead of letting the data tell the story, people spend too much time trying to just contort the data into the narrative that they were looking for.
Right.
And so I think a lot of times you just have to be open to that the data might tell you things that you weren't expecting, or you even just don't like. But you have to kind of have to go where the data tells you you need to go on this one. And in terms of the being ethical, man, I think that's a hard one. I don't think I have a general guide.
Well, if I can just chime in, one thing when I've been learning about statistics is the importance of establishing a clear expectation, so that even if something's statistically significant, people don't skew that data to meet some kind of agenda. If I'm hearing you correctly, just even you trying to kind of connect these dots, it just sounds like you really need to make sure that before you're using something like this, that it's really clear what to expect. As well as, I don't know, putting some kind of guardrails up, because
yes,
as you know, people are always looking for the path of least resistance. It's just human nature.
It is, and they're looking for the that magic solution that they don't have to really think about. They just pop it in and it comes out. So I love what you just said, and that's why I call it augmented intelligence. That's what AI means to me. It's not artificial intelligence. We need to be fully engaged with the answers that it's producing and make sure that it meets our sanity checks, which gets to your, let's understand what we think statistically is in the realm of possible. And if it's an outlier, you can't just go, oh, I guess that must be it. No, it's an outlier. We have to investigate it.
Right. No, thank you.
Any other questions? I see a couple of hands.
That was Liz and Chris here.
Okay.
asked earlier. Pat, I have a question or a comment. I think I've seen this presentation at least once before, and I think you've added a few things to it. How much more complex is the like the facial recognition process than the image classification process?
Okay, so good question, and it depends on the level of accuracy, I guess you're looking for. So let me give you for an example. The packages that I use to do the facial recognition, I wouldn't say is super accurate. It's looking for patterns in your face, obviously, but it doesn't take a lot of three-dimensional aspects of the face into account. So that the algorithm is super fast to train, super fast to run a prediction through, but maybe not as accurate as some of the other ones. So facial recognition is shockingly, at the level that I used it for right here, which works really well, in good light, and you have to have good a picture of a face. If it's not a good picture, it doesn't do well. But so let's say your lighting is good, your input data is good. Shocking, like 20 lines of code and you can do facial recognition. And I only need one picture. I did a blog post a while ago on facial recognition with a single LinkedIn profile picture. So with one picture off of LinkedIn, I was able to do facial recognition with this. So we talk about, you're sort of scared where this is going, and yet each and every one of us, we're not leaking data. It's a fire hose of data that we're just giving away. And people are using it. Every time if you got a driver's license, the government's got your picture. If you got a passport, if you don't think they're using that to somehow, someday, I think they are. So, but we are on Facebook, you're just giving away pictures. When Facebook did their 10-year challenge, it wasn't for fun. They wanted to see how do people age but in a decade so that they can use that data. So oh, the US classification. Again, the same type of a thing, depending on how much accuracy you want. It's literally less than 100 lines of code probably to do image classification on a reasonable set of images. So it's getting to the point where it's not terribly hard, and you can run most of them on your laptop.
Cool, thanks.
And maybe, Adam, if you got a different perspective on that, because you're in that particular field of study, feel free to chime in. That's been my experience.
All right, well, again, if there are any more questions, obviously Brian is looking for hands, but I don't see any, and Brian doesn't either. Pat, thanks again so much. This was outstanding. Maybe we will have you back later in the year for a second episode.
Great. And maybe we could make it just like a discussion of the things that scared us. That was a fantastic set of things. It'd be great, just conversation.
Well, that'd be great on our end as well.
Okay.
So thank you so much, Pat. Everyone, have a great evening. Thank you, Brian, as always. Bye, guys.
All right.
Thank you, everybody.
Bye.
I appreciate you guys being here. Thank you.
Good night.
Thanks, Pat.
Thanks.
Good night.
Night.
Good night, all.
Good night.